All right, hello. Today I'll be talking about like multivariable calculus, just kind of an introduction, kind of thinking about surfaces and multivariable systems, and maybe I'll talk about finding the slope at certain directions of multivariable systems. So basically, what we have to talk about is kind of what does it look like in 3 dimensions. So in 2 dimensions, we're used to just a standard curve where we have either our x-y axis or our polar coordinates or anything, and we have some curve that looks like, it doesn't matter. It looks like some curve, and we call it y equal f of x. And we can analyze the slope of this curve, we can analyze the area of this curve fairly easily, right? Well, in 3 dimensions, it becomes a lot more difficult. And so I'll show some examples of kind of really simple curves. These are like the simplest curves in 3 dimensions that we can imagine. So, we have some curves. So we have like ellipsoids, paraboloids, hyperboloids. These are just a few examples. These are just a few examples of curves in a multivariable system. So, for example, if we had our standard parabola like y equal x squared, and it looks like this, right? This is just our standard parabola in the xy plane. Well, if we were to extend this to another dimension, we would have, some, and I'm going to talk about just Cartesian coordinates right now. We would have, instead of some point x, y, we would have some point x, y, z. So we're basically adding another spatial axis here for Cartesian coordinates. So if we have a parabola here, that's going to turn into a paraboloid if we do the exact same thing, and it ends up being, so z is our output, and we have like x squared plus y squared. So that is, so that's something that basically, this is how you describe kind of a unit parabola in 1 dimension, and this is how you describe a unit paraboloid in 3 dimensions, or sorry, in 2 dimensions and 3 dimensions. So, so how do we describe like points in 3 dimensions? Well, in 2 dimensions, we have our 2 main systems. We have our Cartesian system, and then we have our polar system, which kind of looks like this, and then we have, we have our point r theta, and we basically are saying, okay, we're gonna, rotate some angle and then go out, and that's how we describe a point in the polar system, or we're gonna go, like along the x-axis this far, and then along the y-axis this far, and that's how we describe a point in Cartesian systems in 2 dimensions. But how do we describe them in 3 dimensions? So in 3 dimensions, here are the 3 most commonly used systems. So we have two polar systems and 1 Cartesian system. So I'm going to start with the Cartesian system. So the 3-dimensional system, Cartesian system, is basically the same as the 2-dimensional one, except now we're adding another spatial axis. We're adding the z-axis that goes up, that's perpendicular to both the x and the y-axis. So we're doing the exact same thing. We're going to say, okay, we're going to move along to some point along the x-axis, then some point along the y-axis, and then up along the z-axis. And that's how we describe a point in Cartesian system. So like any, we could have a point, and it's described by x, y, and then z, where most commonly for a function, for a 3-dimensional function, z is going to be our output. And then we have our 2 polar systems. So now, this is where it gets really weird. We have the cylindrical system and the spherical system. So in 1 dimension, this is what our polar system looks like. We just have 1 angle and 1 radius, and our point is defined by r theta. But in 3 dimensions, we have 2 different systems for polar coordinates. One is the cylindrical system, which we have our point in 3 dimensions over there. So we have our some point in 3 dimensions, and here's our axes. And this is I'll leave it blank for now, and then I'll explain it later. So we have our reflected line to this point, right? And the angle from this line, this line to the point, and the z-axis is going to be our angle phi. Sorry, this is really bad phi. And then what we're doing is, here's our x-axis, here's our y-axis, and I'm just basically showing two different systems here to kind of compare the two. So here's our standard Cartesian, we have our x, y, z, and now what we're going to do is we're going to reflect this down, and so now we have a point on the xy plane. So this point, this line has just been reflected down onto the xy plane, and now we have our angle from the reflected line on the x-axis, which is theta. And then we have our radius, which is, instead of r, is described by the Greek letter rho. So we have rho, and then theta, and then phi as our coordinates. And that's one of our coordinate systems. And so this one is basically saying, okay, we're going to rotate a certain angle from the x-axis, and then we're going to rotate a certain angle from the z-axis. And that's why it's called the spherical coordinate system, is because you have two angles, and then you have our total length right here. This length is rho. So it's like, kind of like our radius. Yeah, what is it?
So it's kind of like a shifted triangle.
Yeah, exactly. It's like a triangle kind of rotated into 3 dimensions. Yeah. And then we have our last coordinate system here, our second polar coordinate system, is the cylindrical polar coordinate system. And this one is actually a lot simpler, because this one is acts as the xy. So the xy axis here is just the polar system. We have the exact same thing on the xy plane, where it's just we have any point r theta. And that's our 2-dimensional polar system. But now what we're doing is we're extending this up and creating a perpendicular axis, so going out this way, which is our z-axis. So instead of having 2 angles, we only have 1 angle, because our polar system is on the xy plane, and then it's just being raised up, certain amount. So we're rotating out, and then we're kind of going out a certain amount, and then we're going out a certain amount. Yeah.
All the examples that I've seen you show for multivariable functions that have been graphed seem to be just regular functions that have been rotated around the z-axis. If we're doing more than just that and creating variation, does that require more than one multivariable function, or how does that work?
Well, just like in 2 dimensions, that's actually a really good question. So just like in 2 dimensions, you can have, for example, we have a parabola shifted, we have a parabola rotated 90 degrees, and it's just x equal y squared, right? Now this isn't a pure function of x, right? It doesn't pass the vertical line test, but it is a function of x and y. And so same thing with these examples that I showed earlier here. So, back. Oh, no, that's the wrong one. Okay, so same thing with these examples here. So these are not functions of so some of them, like the parabola is a function of x and y, because it still passes the vertical line test in 3 dimensions. But you can see the hyperboloid there and the ellipsoids, both kind of, they don't. So you're going to describe that kind of thing. Whereas you can describe this using just one equation, but it gives you, if you were to write it in terms of y, you get y equal plus or minus root x, right? So you technically it is split up into separate curves, but you can express it in one equation. So
okay,
I'll give an example. So a circle in 2 dimensions, right, is of the equation of the form x squared plus y squared is r squared, right? And this is our circle, and this is our radius r. This is not a pure function of x, right? We can see that here, but and we can say the exact same thing for a sphere. So for a sphere, it's just x squared plus y squared plus z squared is r squared. And we're just extending this another dimension. Now we can write this as one equation, but we're going to split it up into 2 different functions. Yeah.
I see, thanks.
So now I'm going to be talking about, well, how do you define slope in 3 dimensions? So slope in 3 dimensions is a lot more difficult to define than in 2 dimensions. In 2 dimensions, it's clear. We have one slope here. There's no question whatsoever. But in 3 dimensions, oh yeah, go ahead.
Yeah. So how do you actually graph the parallel? What's the actual function?
Oh yeah. So you can. So right here, like our circle, right, it goes like x squared plus y squared is r squared. And then it goes x squared plus y squared plus z squared is r squared. So that's sphere, just like with a parabola, right? We have y equal x squared. But in 3 dimensions, for the Cartesian system, z is our output axis, right? So we have z equals x squared plus y squared. And so this is the equation that defines the paraboloid, basically.
Okay, thank you.
And so how do we define slope in 3 dimensions? Well, I'm going to give you an example. So if we take a look at this piece of paper here, and I'm going to angle it like this. If I look at the piece of paper from this way, the slope is really high. But if I look at it from this way, it's like almost not changing. So depending on how we look at the graph itself, the slope is actually going to change. And that's why it makes it a lot more difficult to try to differentiate a function in 3 dimensions. And that's why what we have to do is, for a 3-dimensional system, we basically have to reduce it to 2 dimensions to try to find the slope. Because there are infinitely many slopes. And unless the slope is 0, unless there's a local maximum or minimum in 3 dimensions, there are infinitely many slopes, depending on which angle you look at it. So that's why I'm going to introduce the idea of what's called the partial derivative. And there we go. So, as I said earlier, it's pretty much impossible to kind of find the slope in 3 dimensions because there are infinitely many slopes. So, for example, this curve here, as if you look at it in the direction of the y-axis, it's a lot less than if you look at it in the direction of the x-axis. So, what we have to do is we basically have to try to take a slice of this curve, and we're just taking a slice of this curve so we can actually analyze the slope from that slice. So, how do we actually compute this? So, here, if we take a slice of this curve, we're taking it in a slice in the x direction. And so our x is constantly changing. Our x here ranges from any number down here to any number up here. But our y is the same, always. Our y is always the same. And then here, in this example, our y is constantly changing, but our x is always the same. Our x remains constant throughout this example. So how do we actually compute this? So let's say I had some 2-dimensional function, and this is how we write 2-dimensional functions. So in 1 dimension, or sorry, in a 3-dimensional function. So in 2 dimensions, we have some f of x, right? That's our function. But now in 3 dimensions, we have f of x through y, where our point in the Cartesian system is x, y, f of x, y. Just much like the x and then f of x. We're doing the same thing, but we're extending it to 3 dimensions. So how do we evaluate the slope of, let's say, I'm going to give the paraboloid example, z equal x squared plus y squared. How do we, and z here is a function of x and y, just like if I were to say y equal x squared, y equal f of x. So how do we analyze the slope? Well, the slope is different depending on how we look at it. So for simplicity, we're going to, the 2 simplest ways to look at it is if you look at it in parallel to the x-axis or parallel to the y-axis, which are the 2 examples there. So how do you analyze,
So basically you can't really solve for it when you have 2 variables, so you just set the change of one of the variables to 0 and then just analyze it with just 2?
Because you cannot, the slope, depending on how you look at the point, the slope is completely different. So that's why we have to cut a slice in the x direction or the y direction, or even later, I'm going to talk about in a few weeks in any direction. But for simplicity, I'm just going to talk about the x and y direction.
But then what would you call the slope then? So would you just say the slope with respect to just the x direction?
Exactly,
and with respect to the y direction?
Yeah.
So there's no there is no set slope for that point. It just depends on how you look at it.
Yeah, exactly. So there's no set slope for that given point. So how do we, for example, for this function here, how do we differentiate this? Well, we know if we had some function y equal x squared, the derivative is going to be 2x, right? That's just based on our derivative rules. Well, how do we do that with this? Well, here, how do we differentiate this, for example, in the x direction? Well, in the x direction, we can see here, our y value remains constant throughout the entire thing. So we're going to treat y here as a constant. And what happens if we differentiate a constant? It just goes to 0. So we're going to say, okay, if we differentiate this with respect to x, so our x is constantly changing, it's just going to be 2x. But then if we differentiate this with respect to y, oh yeah,
Oh, and we can just treat that as a constant because we're not evaluating it in this particular case?
exactly, yeah. And so if we like differentiate this with respect to y, we end up getting 2y. So that's why I'm going to introduce the idea of a partial derivative. So this is exactly what a partial derivative is. I just did a partial derivative with respect to x, partial derivative with respect to y. And in a normal two-dimensional system, we just say, okay, a dy dx is equal to y prime. We can't do that because we can't have a complete derivative, right? So we say we're going to do a partial derivative of z with respect to x. And this symbol is exactly, you treat it exactly like the d, but it's a del. And it's just saying, okay, we're going to differentiate a three-dimensional function in one direction, or, you know, del z, del y. And so for this function, this is del z, del x, this is del z, del y. And so that's kind of the idea of a partial derivative, because there's not one given slope, there's infinite numbers of slopes. So that's why we have the partial derivative, and that's why it's so important to kind of analyze this and break it down into two-dimensional surfaces instead of a three-dimensional surface. All right, does anyone have any questions?
That makes sense. So del is just the derivative sign, but for
Yeah.
partial derivative.
Yeah,
That
exactly.
makes sense.
And now I'm going to introduce the last idea. So basically, just imagine if we were to sum up all of the infinite numbers of tangent lines on any direction, not just the x and y direction, but every single direction. We summed up all the tangent lines, what would we get? We would get a plane. And so much like a tangent line, like in 2 dimensions, where we have some function and then we have a tangent line here. In 3 dimensions, we have a tangent plane. And this tangent plane basically shows the slope at any direction. So, oh, that's really hard to see. Okay. Yeah. Anyway, so the tangent, tangent plane is much like the tangent line, right? And so if we were to say, okay, I'm going to differentiate the tangent plane in the x direction, that would give us our slope at the point, or in the y direction, our slope in the y direction. So it's basically we're adding up like infinitely many of the tangent lines, and that sum of infinitely many tangent lines creates a plane. And
Would it be the sum or the multiplication of the two different tangents?
it would be the sum, because you're adding like a tiny slice at another tiny slice, and at infinitely small increments, right? You create like a sum of lines, which creates a big plane.
I see.
So that, yeah, the images are really bad. But kind of a general idea here. So it's hard to see, but here we have some, I don't know, sphere or something, some surface, and we have a plane going tangent to this point x, y, z. And so how do we actually compute this plane? Well, much like a line in 2 dimensions, so I'll erase this. So much like we have a line in 2 dimensions, and our line is described by just y equal some, I'm going to say constant x plus constant 2. And I'm not going to say mx plus b, just because for simplicity, I'm going to explain the next one. So just like we have a parabola that goes from y equal x squared to z equal x squared plus y squared, our equation for the line would be kind of the exact same pattern, which would be z equals constant 1x plus constant 2y plus constant 3, where this just shifts our graph up and down to make sure that it actually is touching the point. And this is our slope in the y direction, so in the x direction. So if we were to basically differentiate, if we were to find, okay, a del z, del x, we would end up, this is a constant, this is a constant, so this all goes to 0. And that would just be constant 1. So our slope in the x direction is constant 1. Our slope in the y direction is constant 2. And this right here, just we would plug in our point x, y, z, and we would output this point to make sure that this graph truly is tangent. So how do we, for example, the tangent plane to the graph, I'm going to give the same example, z equal x squared plus y squared. So this, how do we find the tangent to the graph at point, I don't know, 1, 1? I'll make it really easy. So if we differentiate this with respect to x, what do we get? This, if we just differentiate z equal x squared plus y squared. All right, what do we get as our, yeah, just 2x, right? So del z del x, this is 2x, and then del z del y.
It's just 2y.
Yeah. 2y. And so at our point 1, 1, our slope is 2. Our slope in the x direction is 2, our slope in the y direction is 2. And so you would have z is equal to like 2x plus 2y plus constant 3. And so I'm going to wrap it up there. So this is kind of just the general form of a plane tangent to any surface. And that's just kind of the idea. It's just kind of thinking about it in 3 dimensions, just like a tangent line is in 2 dimensions. And then next week, I will talk about not finding the slope, but not finding the area like I am in 2 dimensions, but finding the volume in 3 dimensions. All right.